Welcome back. In this video, we'll teach you how to pick u in integration by parts. And the trick that I'm going to give you is called LIATE. All right, so when applying integration by parts, we exchange an integral for a hopefully, that's if you choose the right u, simpler one. So really, if you look back at the formula for integration by parts, this is the one we start with, and we end up having to evaluate that one. So hopefully this one should be easier. Otherwise, then you scratch this and you go back to the original one. All right, so if you apply integration by parts, you're exchanging the integral of u dv with the integral of v du. So you have to take u and differentiate it. So you want to pick u a dv so that u has a simple derivative. So hopefully this will be simpler than this. And then the second thing you'll have to do is you'll have to integrate to go from v to dv. All right, so you need dv to be integrable. If you don't know how to integrate dv, then you can stop right then. That's not right. So is easy to integrate. If it has a simple integral, that's even better, but if it doesn't, if you don't know how to integrate it, you're wasting your time. All right, so in the functions we know, amongst the function we know, logarithm and inverse trig function are hard to integrate. In fact, if you notice, this last example, I integrated just log, and I had to use integration by parts, and I got this mess here. All right, so logs and inverse trig are hard to integrate, but they have nice derivatives. I'd rather have 1 over x than log of x in my integrals. So these are going to be amongst the best u. So if you have logarithms, or if you have inverse trig function, if you have them inside your integral, those are going to be your u. So they will therefore be u whenever they appear in your integrals. Now, exponential and trigonometric functions barely change when they're being integrated or differentiated. So if I have an exponential, if I have e to the x, they're not going to change, and so they don't have a simpler derivative, but they're easy to integrate. In fact, the integral will not be more complicated than what you started with. It's not really changing. And so these will be good dv because they're easy to integrate, but not great at u because they don't simplify. So if you have trigonometric functions or exponential, then you should not pick them as u. And then I have one spot in the middle. That's going to be for anything that's like an x to the k or a polynomial. So I'm going to call them algebraic. And by that, I mean x to the k, so even roots, and then polynomials, roots, something like that. If you have x squared, then the derivative is 2x. It is simpler because the degree is less, but not much simpler. It's not a completely different type of function. So when you have an integral and you want to apply integration by parts, you go through the list, and here's the LIATE: log, inverse trig, algebraic, trigonometric, and exponential. The one that's higher up, that's going to be your u. The one that's lower, that's going to be your dv. These are better dv, these are better u's. All right, so let's try to apply this technique to a couple of integrals. Let's look at example 3.3.3. Evaluate the following integrals. All right, so I have the integral of ln of x over root of x. All right, first thing, I'll write it as a product. I don't like the fact that it's a quotient. In integration by parts, I have a product of functions, and so I'm going to write it as x to the minus a half log of x dx. Once I've done that, I can see that I have a log here. So this is an L. And here I have some power. You can even think of it as a root. So I'm going to have an algebraic. Log is first, so that's going to be your U. A is lower, so that's going to be your dv. So when I apply integration by parts, my U will be log of x. My dv will be x to the minus 1/2 dx. I'm going to differentiate log of x. I'm going to get 1 over x dx. And I'm going to integrate x to the minus 1/2. I'm going to get x to, I add 1 and plus 1. And this is what I get. All right, so I'm going to take this product minus this integral. So I'm going to have x to the 1/2 log of x over 1/2 minus the integral of x to the 1/2 1/2 1 over x. All right, so let me simplify this a bit. That 1/2 I'm going to bring to the top. It's going to become 2. I'm going to rewrite root of x because I find it easier than writing x to the 1/2. Now these cancel partly, and I'll be left with 2x to the minus 1/2 dx. And now this, much simpler to integrate than what I started with. Yeah? All right, so having 1 over x is super nice if you have polynomials, because then you can just simplify them and you get another power, and powers are easy to integrate. All right, so I get 2 root of x log of x minus 2x to the 1/2 over 1/2 plus c. Don't forget your plus c as soon as you evaluate your last integral. So I get 2 root of x log of x minus 4 root of x plus c. All right, I'm going to do one more. I'm going to do the integral of x squared plus 1 cos of x. All right, and then we'll stop this video. Here, let's look back at our list. Well, cosine is trig. That's easy. And then x squared plus 1, that's a polynomial, so it's algebraic. So this part is A. So A is higher up than T, so that's going to be my U. Whatever is higher up, that's your U. So this one's U, this one is dV. All right, so we said U was x squared plus 1, dV was cos of x. dx, you differentiate this one, you get 2x dx. You integrate that one. The integral of cosine is just sine. All right, and so we get x squared plus 1 sine of x minus 2x sine of x dx. All right, so let me move this a bit so I have more room. Let me shrink it a bit. Yep. All right, so this product minus this product. Now I have a new integral. It's still a product of a polynomial times trig like I had here. So at first glance it doesn't look simpler, but notice that the degree of the polynomial has gone down. I had degree 2 here, now I have degree 1. And so applying integration by parts did simplify my integral just a tiny bit. I'd like to get the degree even lower, get it to 0, and so it feels like I need to do this again. All right, so I still have A and I still have T. So I'm going to reapply it. I'm going to do U equals 2x, and I'm going to do dV equals sine of x dx. All right, so du is 2 dx, and v is, so I want a function whose derivative is sine. If I take just cosine, that's going to give me minus sine, so I need an extra minus. All right, so I'm going to take this product. So I'm going to take 2x times minus cos of x, and I'm going to subtract this integral. So subtract the integral of 2 minus cos of x dx. All right, so the degree has gone from 2 to 1 to 0. Now it's just a constant. I can pull it out front, and I will get a basic integral. 2, and then integral of cosine is sine, so I get minus sine. All right, so one thing that we'll talk about in the next video is whenever you have to apply integration by parts more than once, like this, something interesting happens. If you look at this column here, so let me highlight it for good, and if you look at this column, it's exactly the same. And so what we'll learn in the next video is there's a way of skipping this step altogether, writing, sorry, didn't mean to do that permanently. So skipping this step, I'm going to write this, this, and this, and I'll be able to come up with this directly skipping this step. And it's going to make it faster, much faster to integrate complicated combination of trig and trig and trig, trig and exponential, and trig and polynomial, and exponential and polynomial as well. All right, so I'll show you that next time.